Hello. So we'll wait for a couple of more minutes and then we'll start. So, do you have any questions or doubts so far? Kalpana, do you have any questions? What about Aryan?
Yes, ma'am.
Yeah, you have any questions or doubts?
Yes, ma'am.
Okay. So, can you tell me what doubts you have?
Yes.
Okay, so since we've it's been some time since we waited, so we will start the class now. So, welcome to the live session for week 4 of Basic Environmental Engineering and Pollution Abatement. I am Niketa and I am a PhD student at IIT Madras. Okay, so are you able to see my screen?
Yes, ma'am.
Okay, so what I'll do is I'll just give you a brief overview of some selected topics from the previous week's lectures, and then we will discuss some MCQ type questions. Okay,
Okay, ma'am.
so first, sampling. So, what do we mean by environmental sampling? So, like what we will do in sampling is we will basically collect samples from any environmental media. It could be from maybe it could be from air, water, or soil samples. So why we collect samples is we want to analyze them for any presence of any contaminants. In the environment. So, and when we collect samples over a period of time, then it is called monitoring. So, environmental monitoring is so this means that we are collecting samples for a period of time. For example, say 2 years or 3 years, we collect regularly at certain intervals, maybe once in a week or every day, we collect samples and we again go back and collect samples just to make sure that there are just to check if there are any drastic changes in these parameters or not. So that is environmental monitoring, and sampling is a part of this monitoring. So coming to air sampling. So in air sampling we have two types. The first one is grab sample. So grab sampling is just as the name suggests, it is just grabbing something. So we just have to grab something very quickly. So this kind of sampling is collected very quickly, and it is stored in a container. So this grab sampling is not a very meticulously done. It is just going and collecting. Suppose you have a river, just going there and taking a container and collecting the sample and coming back. So it's not like we have to do it every 3 hours, 4 hours. It's not like that. We can just go and collect the sample and come and analyze. So this is useful when our sample, the parameter that we are analyzing will quickly change with time. The second type of sample is sampling is integrated sampling. So this is basically grab sampling, which is done over a period of time. So multiple grab samples. We will collect some, say, 3 or 4 samples, and we will take the average of them. So this will be the integrated sample. So So this is the average of graph samples, and it is done over a long period of time. So usually, yes,
used for long term लास्ट में क्या लिखा था मैम
studies.
स्टडीज
Yeah. So it is done over a period of maybe say 24 hours to 48 hours. Like usually it is done for 24 to 48 hours. So every hour we'll do some monitoring. We will take samples and we will just analyze the results and check for the presence of contaminants and what is the concentration of those contaminants. That will be checked. So since this needs to be done over a period of time, it is very different from grab sampling, which is done instantly and very quickly. Okay.
में टाइम पीरियड इसका 24 to 46
Sorry.
ये इंटीग्रल सैंपलिंग में 24 is equal to 46
24? No. I said 24 to 48 hours.
48 hours
Yes. Okay. And then we have something called, there are two types of sampling. So one is direct sampling, which is just sampling as it is, just taking the sample and not doing any modification. So this will be sampling as it is. And then there is indirect sampling. So this will do some, in this indirect type of sampling, we will do some modification. Like we will take some, we will just absorb the sample using physical absorption or chemical absorption. So that is called indirect sampling. So some kind of sampling absorption is involved. So that's why it's called indirect sampling. So indirect sampling again can be divided into two categories. Physical absorption, using physical absorption. So the pollutant is, in this one, the pollutant is dissolved in a liquid and it is analyzed. So and the other one is chemical absorption. So in this one, the pollutant reacts with the absorbent and the resulting product will be analyzed. Okay. Then
केमिकल एब्जॉर्प्शन के इक्वल टू पॉल्यूटेंट के बाद क्या लिखा है मैम ये
pollutant reacts with the absorbent.
reacts with absorbent
Yes.
okay.
Then we have absorption of gas and liquids. So here we have the bubbler and impinger type of device. So it is very simple and the gas is just bubbled into the liquid. So that will ensure that the gas is getting absorbed into the liquid. So the first one is the bubbler and impinger type. And the second one is the so here we have the gas analyzer for carbon dioxide, oxygen, and carbon monoxide. Okay, and this is an example. These two are examples for absorption of gas in liquids. Other than this, gas can also be absorbed onto solids also. So, one example of, have you heard of this term called activated charcoal? It is a very good absorbent and it absorbs mostly uh, volatile compounds or organic compounds. So, this can be used as an absorbent for absorbing gases, and this is an example of absorption of gases in solids. So, now, when it comes to sampling of air, there is one more type of sampling which is called freeze out sampling. So here, if we have different types of gases, based on their condensation temperature, they can be separated. And then we also have sedimentation. So sedimentation is used for collecting particulate matter which is greater than 1 second. So sedimentation is used for collecting particles which are greater than 10 micron in size.
टेन लिखा 10 लिखा है मैंने
Sorry,
ये कलेक्टिंग पार्टिकल ग्रेटर देन 10
mu micro.
माइक्रो हाँ
Yeah, micrometer.
ओके
Okay. So this will consist of a funnel type of an object, and this will, this will look like this. So whatever particles are there, it will come out, and the heavier particles will be settled at the bottom, and it will come out. So the weight, that which is more than 10 micron will pass. Sorry, that which is less than 10 microns will pass, and which is, slightly greater than 10 micron will be retained. So that can be collected, and the weight will be determined. So, in air pollution, one of the major types of air pollutants is particulate matter. So, for sampling particulate matter, in particulate matter, we have two
मैम
types of.
आवाज
Yeah.
ब्रेक हो रही है बहुत.
You have a question? You have any questions? Okay, so for sampling particulate matter, there are two types of samplers used. One is the high volume sampler. So can you tell me what is the capacity of a high volume sampler? How much volume it can take? How much volume of air can be sampled using a high volume sampler? Okay, so in a high volume sampler, up to 2000 meter cube of air can be sampled. And this can be done in 24 hours. So the mechanism here is that we will have a motor and there will be a suction device. So using suction, this sampler will intake the air samples. And also at the inlet we will have a filter. So this filter will ensure that when air gets sucked in, the particles get deposited on the filter. So it will have a porous filter to ensure that the material is getting impacted on it. And then we have a tape sampler. So tape sampler is just like a tape. So it's more like a ribbon. So a pump will be kept here so that then a suction force will be applied and therefore the particles will be deposited and they will be collected and their weight will be checked. So this is a tape sampler. So then coming to the different types of sampling mechanisms. So what are the different sampling mechanisms that you know? One second. So what are the different types of sampling mechanisms available for air sampling, especially for particulate matter? What is the mechanism that comes into play when you want to sample a particulate matter using a filter? So the first mechanism is by impingement. So here impingement means that the particle is colliding with a flat surface. And this is mostly used in the liquid phase. And especially it is useful for collecting particles whose size is less than 2 microns. It is useful for collecting particles whose size is less than 2 microns. And that too, we use a wet impinger. So the reason why we use a wet impinger is because sometimes in the presence of water will attract the pollutants better because of some interactions between the surface charge. So that is why sometimes a wet material will attract more dust. So that is impingement. Basically, it's just collision through a flat. If you have a flat surface, the particle comes and just collides with this. So that is impingement. And the second type is electrostatic precipitation. One second. So, what is electrostatic precipitation? This is a very popular method for collecting particulate pollutants. So, can someone explain what it is? Just the basic idea. Anyone? Okay, so in electrostatic precipitation, you have two plates, and both of these are connected to a power supply. So, because it is connected to a power source, it will be charged, and one of the plates will be positively charged, and the other one will be negatively charged. So, whatever dust particles are there, depending on their surface charge, so mostly if the dust particles are negatively charged, they will be attracted to the positive surface and they will get deposited here. And once you turn off the power, their attraction will break, and whatever deposited particles were there, they will get collected here at the bottom of the plates. So the collected particles can be then removed. So this is electrostatic precipitation, and this is used for particles in the range of 0.01 to 20 micrometers. And this is also suitable when you have a high particle loading. So when you have high particle loading, your impingement will not work because like mostly in the case of filters, when there are high particle loading, the filter pores may get blocked. So in such cases, electrostatic precipitation is a very good choice. The next type is thermal precipitation. So in thermal precipitation, we apply a temperature gradient. So like one end will be heated. I mean the temperature at one end will be higher than the other end. So here the temperature will be slightly higher. And here it will be lower. So generally particles will get attracted to a lower temperature, so it will get deposited here and then it can be collected. So this is suitable for particle size of 10 to 0.01 micrometer at flow rate of 10 to 200 ml per minute. So there is a gradient here. So the temperature varies from a high end to lower end, and the particle will get attracted. It will get deposited towards the lower temperature. Okay. So next, after collecting all the samples, we look at what are the analysis methods. So first one can be UV photometry. And the second one is chemiluminescence, where NO2 is converted to NO, which later reacts with ozone, total NOx, and because of this, the total NOx and NO and NO2 can be analyzed. So chemiluminescence. And then we have the non-dispersive IR. Then we have gas chromatography. So in the previous class, we have looked at these things: gas chromatography, UV photometry, even HPLC in detail.
So all these methods can be
So
used
all
to analyze
these
air
methods
pollutants.
can be used to analyze air pollutants.
Okay. Coming to
Okay.
water.
Coming to water.
So in water,
So
mainly
in
we
water,
measure
mainly we measure
dissolved oxygen,
dissolved oxygen,
BOD,
BOD,
COD,
COD,
total
total
solids,
solids,
and
and
volatile
volatile
solids
solids
and
and
all.
all.
So
So
can
can
someone
someone
quickly
quickly
tell
tell
me
me
what
what
is
is
the
the
saturated
saturated
dissolved
dissolved
oxygen
oxygen
concentration
concentration
in
in
water?
water at 25 degrees? So what is the saturation concentration of oxygen in water at 25 degrees Celsius? Okay, it is somewhere between 8 to 9 milligrams per liter. Okay, so coming to DO measurement. So for this, we use a method called Winkler's method. So in this, what happens is your Mn2 plus will get oxidized to MnO2, and the MnO2 will then react with iodide and it will produce iodine. So the iodine produced will be measured using titration, and that iodine produced will the amount of iodine that is produced will be equivalent to the amount of oxygen which was present in the sample. So what this is, so in the presence, Mn2 plus will react with oxygen and it will give out manganese oxide, and this will happen in the presence of I minus and hydroxide ions. And since whatever oxygen was dissolved in the sample, that will only convert Mn2 plus to MnO2. And after converting to MnO2, this MnO2 will react with iodide ions in the presence of an acid. So that's why we have the H plus ions. This will give Mn2 plus salt plus iodine and 2H2O. So then we will determine the concentration of this iodine using titration. So we will use sodium thiosulfate, and starch will be the indicator. So the reaction that happens during titration is thiosulfate will react with iodine and it will form S4O6 plus two iodide molecules, and so the number of iodine that was consumed in this reaction, if you see the number of moles of iodine, Here, 1 mole of iodine is getting converted to 2 moles of iodide, and the number of moles of iodine is equal to the number of moles of oxygen here. Both are 1. Therefore, we can say that the amount of iodine, number of moles of therefore, if we know how much of iodine is used for this reaction, we can easily find out what is the concentration of the oxygen. So let's do. So if we know how many moles of iodine has been used for this reaction, that many number of moles of oxygen were there in your sample initially. So that is Winkler's method. And then for measuring the biochemical oxygen demand, so can you tell me what is biochemical oxygen demand? What is BOD? So what is BOD? Okay. BOD or biochemical oxygen demand is the oxygen that is required by the bacteria to oxidize the organic pollutants. Okay. So, in order to do this, we need bacteria to be present in the sample. So, sometimes what happens is in some industrial wastewaters, we may not have any bacteria at all. Zero. Like there is sometimes in some industrial wastewaters, there will be no bacteria. So, in that case, what we do is we have to give the bacteria to the sample. So, how do we do that? We do it through a process called seeding. So seeding is just addition of bacteria to the sample. And this will be taken using many sources are there like cow dung or raw sewage or even sludge. So all this will be having bacteria. So some of that is taken and it is added to the sample. Why we do this is because if we don't have any bacteria, then there will not be there won't be any oxidation. So if there is not going to be any oxidation, then there won't be any oxygen demand. So in order for the reaction to take place, we need bacteria there. So that is why we are supplying it externally. So this method is called seeding. And to measure the BOD, we first the wastewater sample is diluted. And then it will be seeded. The bacteria will be added. So we will be measuring the dissolved oxygen content 2 times. The first one will be right after you add the bacteria. Immediately we will be measuring the dissolved oxygen. And then once again after 5 days we will be measuring the dissolved oxygen content. So why we are measuring after 5 days is we are giving the bacteria time to oxidize the pollutants. And during the 5 days, the sample will be incubated at 20 degrees Celsius. So at this temperature, we will keep our samples for 5 days, and we will measure the DO of the sample after the end of 5 days, and then we will calculate the biochemical oxygen demand. So in case if we want, we can even instead of taking the sample after 5 days, we can even take the sample after 3 days at a higher temperature, that is around 27 degrees Celsius. Now the formula for in case we have unseeded samples, then the formula will be BOD5, which is the BOD after the 5 days, equal to dilution factor into DO at T equals to 0 minus dissolved oxygen at T equals to 5 minus dissolved oxygen at T equals to 0 minus. Now this is for the sample. Now while we are doing this, we will also take one blank sample which does not contain any wastewater, and it is just having bacteria. So there will be slight changes in the DO in the blank sample as well. So that is why we are taking that also into account. So this is DO at T equals to 5. So after 5 days, whatever DO is there in the blank sample, that also we have to subtract. Now if you have a seeded sample, where you have externally added the bacteria, then the BOD5 equals to the dilution factor multiplied by DO at T equals to 0 minus DO at T equals to 5. So this is again for sample. This should be subtracted, we have to subtract the DO change in the blank sample from this. So DO at T equals to 0 minus DO at T equals to 5 multiplied with your some factor F. So this factor F will correspond to the seeding. So F is the seeding factor, so which is the volume of seed in the dilution solution. So generally we will do some dilution because as it is, the wastewater will have a very high BOD, and sometimes what happens is when the BOD is very high, the oxygen may not be enough, and that's why the bacteria will die. So to avoid that, that is why we are diluting the sample. So that's why we are taking this dilution factor. So the dilution factor is usually given in terms of like volume of the final volume of the sample, volume of the diluted water by the volume of sample. So suppose I am having after dilution, the sample volume is 300 and I have taken 5 ml of sample, then the dilution factor is 300 by 5. So this means that we have done 60 times dilution. Sometimes what happens when we do BOD test is if the BOD is coming to less than 0.2 milligram per liter, then we will not consider this test, because this means that whatever oxygen was there was consumed. I mean, the bacteria does not have sufficient oxygen. Sorry. It means that there is like the BOD difference between the initial and final BOD is only the difference between the initial DO and the final DO is only 0.2 or lesser. It means that the bacteria has not fully oxidized your contaminant, and therefore it will need more oxygen. So this signifies that less oxygen availability. And similarly, the difference between the initial and the final DO this should also always be greater than not the difference. So the DO after the 5 days should be always greater than 0.2 milligrams per liter. This is because like if you have very less oxygen, then it means that all your bacteria will die. So that's why this will have to be higher than 2 milligrams per liter. Any questions so far? Okay. So then we will see about COD measurement. So this is like the basic principle behind this is the organic compounds will get oxidized in the presence of dichromate and sulfuric acids, and once the oxidation of organic happens, it means that whatever dichromate is there, which is in the form of Cr6 plus, it will reduced to Cr3 plus. So the amount of Cr3 plus will be corresponding to whatever organic compounds were there which got oxidized. So if we know how much of chromium 3 plus is there in the solution, then we can find out how much organic compounds were there in the solution. How much of organic compounds got oxidized. So for that we have to we have to determine how much of chromium 6 plus is there in the solution, because whatever chromium 6 plus was got oxidized to Cr3 plus, some remaining Cr6 plus will also be there. So if we find out how much of Cr6 plus is there, then that will if we subtract that from the initial Cr6 plus, then that will give us how much of Cr3 plus has been formed. So that is what we will do. So the remaining Cr6 plus is titrated with ferrous ammonium sulfate. with ferroin indicator. And COD is given as 8000 into B minus S into N by the sample volume. Okay, coming to then TOC measurement. So TOC is nothing but total organic compounds, total organic carbon, sorry. So TOC is nothing but total organic carbon. So this will give us, unlike the COD or BOD, which will tell us how much of carbon is, how much of organic carbon is getting oxidized. Using TOC, we can directly determine how much of organic carbon is present. So what we'll do in this method is the organic. First the sample will undergo acidification. So in the presence of acid, in the presence of acid, inorganic carbon like carbonates and bicarbonates.
सर्टिफिकेशन लिखा है
हाँ
सर्टिफिकेशन लिखा है
सॉरी
ये टोटल ऑर्गेनिक कार्बन के नीचे फर्स्ट वाला ऑप्शन क्या लिखा है
acidification.
एसिडिफिकेशन
Yes.
ओके मैम थैंक यू
So carbonate and bicarbonate will get converted and it will get oxidized to CO2 and it will be removed. And once we remove all the inorganics, then we will take the organic compound and the organic compounds will be oxidized at a high temperature at about 900 degrees Celsius, and this will also get converted to carbon dioxide, and the converted carbon dioxide will be measured using non-dispersive IR or NDIR. Okay. So whatever organic compounds were there, whatever organic carbon was there, that will get heated at 900 degrees Celsius and it will get converted to carbon dioxide, and the carbon dioxide gas will be analyzed using NDIR. So this will give us a complete idea of the total organic carbon that was present in the sample. Okay, coming to total solids and volatile solids. So in the previous class, we discussed about the various types of solids in water and wastewater. So total solids will include both so this will include fixed solids and volatile solids. So in order to determine the total solids, we will take a filter paper and we will pass the water through the filter paper, and the filter paper will be dried at 105 degrees Celsius. Sorry, not the filter paper, the entire sample itself will be we use the filter paper to determine suspended solids, but since we are talking about total solids here, we don't need to separate it into filtered or into suspended or dissolved. We can just directly take the sample of water and we can dry it out at 105 degrees Celsius. And whatever residue is there, that is taken, the weight of that residue is taken along with the weight of the dish. So the total solids is A minus B by the sample volume. Or how much ever volume of sample you have taken, which has become dry, that volume is supposed to be noted down. So here A is the weight of solids after evaporating the water plus the weight of dish, and B is the weight of the dish. So if you subtract this, then you will get the weight of the solids, and then that will be divided by the sample volume. So you will get the total solids concentration in mass by volume or milligrams per liter. Now for volatile solids, similarly we have to heat the sample, but the temperature at which the sample is heated will be higher. So basically what we want to achieve here is we want to evaporate all the volatile solids present, and then we want to check the weight of the sample before and after the volatile solids have evaporated. Second. Yeah. So we want to check the weight of the sample before and after the volatile solids have evaporated. So that will tell us after evaporation the weight of the sample will reduce. So then we can determine how much volatile solids were there which got escaped or evaporated. So for this we have to heat the sample at 550 degrees Celsius. And the volatile solids concentration is given as A minus B by sample volume into 100. So here A is the weight of the residue, plus dish before ignition. Now here determining volatile solids needs to be done after evaporating the water. So first total solids will be done where the water is fully evaporated, and then we will do the volatile solids test. So this is because we don't need to add or subtract the water weight unnecessarily. So that is why we are considering A as the weight of the residue and dish before ignition, that is before heating at 550 degrees Celsius, and B is the weight of the residue and dish after ignition. Any questions so far?
No, ma'am.
Okay. So now coming to solid wastes. So there are two kinds of properties of solid waste. The first one is physical properties. And then we'll go to the chemical properties. So first, can you tell me some physical properties of solid wastes? What are the physical properties of solid waste?
Density, ma'am, per unit to I think.
Yeah, can you repeat that?
Density per unit volume, ma'am, kg is equal to meter cube.
You mean mass per unit volume, which is density?
Yes, ma'am, mass per unit volume.
Yeah. So first is density, which is mass by volume. So density can be, it is also known as specific weight. So it can be the bulk density, which is one type of density, and the next one is absolute density. So the difference between these two is that bulk density includes the pore volume, and absolute density excludes the pore volume. So therefore, usually the absolute density will be slightly higher than the bulk density, because when we say mass by volume, if we exclude the pore volume, generally solids will have, like, when you have
Ah,
solids. Any questions? Do you have any questions? Okay, if you don't have any questions, can you please mute yourself?
मैंने बल्क डेंसिटी के इंक्लूड प्योर वॉल्यूम मैंने इसके नहीं सुना।
I'm sorry, I'm not able to hear you.
ये बल्क डेंसिटी है मैम।
Yes. Okay, so generally what happens is when we have solids, usually if they are packed together, there will always be some kind of pore. Pores are just gaps. So here we have um, so these gaps here, these tiny gaps here are called pore. So and in this pore, the water or air will be present usually. If it is saturated, it means that the pore is completely filled with water. If it is unsaturated, it means that some pores are filled with water and some pores are still filled with air. So, um, when we calculate bulk density, we'll also consider the pore volume. So, when we say density is mass by volume, if you consider the pore volume in your density formulae, so in the denominator, if your volume includes the pore volume, so your density will be higher or lower. Will the density increase if you increase the pore volume? If you include the pore volume in the formula? Is my question clear?
यस मैम।
Yeah. Can you give me some answer?
केजी पर मीटर क्यों?
No. My question was density is mass by volume. So if I include the pore volume in this formula, then the density will increase or decrease. So here I'm considering the volume of the solids. Solid is, I mean, the volume of the particles that are here plus the volume of pore. So if I say that this volume in the density formulae is the sum of the volume of solids and the volume of the pore, then the density, and this is the formula for bulk density.
बल्क डेंसिटी
For absolute density, can you please mute? Here In absolute density, the volume is only the volume of solids. So in this case, which density will be higher? In absolute density, we are not considering the volume of the pore. We are only considering the volume of the solids that are present here.
The pore volume is completely
Excluded. So if we exclude the pore volume in the calculation of absolute density, this will be higher or lower than the bulk density. Since your denominator is going to be slightly lesser when compared to that in bulk density, obviously the value of density that you are getting here in absolute terms will be higher. So the absolute density will be higher than the bulk density always, because your volume that you are considering is comparatively lesser. You are only considering the volume of the solids and excluding the volume of pores. So that's why the denominator will be less, and therefore the absolute density is going to be high. Okay. The second physical property is particle size distribution. So what is particle size distribution? Can someone answer? What is particle size distribution?
मैम इसमें हेलो
Yeah.
यस मैम मैम बेस पार्टिकल रहता है इसमें मैम साइज और रेंज में रहता है वैसे
Sorry.
मैम डिजाइन रहता है डिजाइन एफिशिएंसी कलेक्ट रहता है और वेस्ट रहता है पार्टिकल में सॉलिड वेस्ट रेफर
No, actually, particle size distribution is we will determine how much weight of each size of particle is there. So, like you can have particles of different sizes in a solid waste sample. So we will segregate them based on their size, and we will determine the weight of each of them. So we will first segregate. So we will segregate the sample based on the particle size, and then we will take the weight of each. We will take the weight of particles corresponding to each size, and then we will make a diagram of particle size versus weight of each size. So that is particle size distribution. And for segregating the particles, we can use different equipments. One of them is using a sieve. A sieve is basically like what you use at homes to to refine the wheat flour. So that is an example of a sieve. So you will have many different sieves stacked one below the other. So starting from the highest pore size will be at the top, and slightly lower, and then lower, and then very fine particles at the bottom. So the pore size at the top will be higher than the ones at the bottom. So whatever comes to the bottom will have a very fine particle size, and in between, in different sieves, based on the size of the particle, the particles will get retained. So that is sieve analysis. So sieve analysis is a type of measurement of particle size, and this is used when the particle size is slightly lesser. For like fine particles, this can be used, but if the particle size is bigger, then we can have screens like trommel screens. So trommel screens are basically cylindrical objects which can be rotated from one end or both ends. It will have screens here. So when you rotate this, when you rotate the screen, when you can open one of the ends and put your solid waste inside. So whatever waste is there, it will some will pass through the screen, and some will just get retained there. So this can separate particles of different sizes based on the size of the screen that you use. And the next property is hydraulic conductivity. So hydraulic conductivity is the ability of porous media to conduct water. And this will be affected by the size of the pores, particle size, etc. So why does hydraulic conductivity matter when you have a solid waste? Why does it matter? Like hydraulic conductivity, what? Because it's a solid sample, right? It's not a liquid sample, and the contaminant is not even in the liquid phase. Then why do we have to measure the hydraulic conductivity? Any idea? So in one of the classes we discussed this term called leachate. So leachate is the liquid that is generated in landfill sites, usually because as waste decomposes, it will release a liquid. So that liquid is called a leachate. And when you have a huge dump site like this, you have soil layer, and when you have a dump site with so many wastes inside, so the some waste which is present in the inner part will get decomposed, and it will start secreting a liquid. So this liquid has to pass through the solid waste and it will come to the bottom. And if the landfill is not secured, meaning that if the landfill below the solid waste, if we don't have adequate layers of protection like HDPE sheets, then what happens is this liquid will penetrate through the soil and it will reach the groundwater. So this liquid that is produced is called a leachate, and in order to percolate through the solid waste, it needs enough hydraulic conductivity. The solid waste should have hydraulic conductivity, which should be enough to let the leachate percolate through it. So that is why we measure this. The next property is the moisture content. So, what is moisture content? It is the weight of water divided by the wet weight of the waste. Into 100. So if you note here, I've used the term wet weight. So there are different kinds of weights. Uh, like wet weight means the weight of the waste before drying, and the dry weight means after the solid waste has been dried and all the water has evaporated, that weight is called the dry weight. So when we calculate the moisture content, since we are calculating the moisture present in the waste, we assume that the waste is wet, and therefore we will calculate the wet weight of the waste only. So you won't calculate the dry weight. So, 1 second. So there are two categories of, two ways in which moisture content can be measured. One considering the wet waste and the other one considering the dry waste. But here we are calculating using the help of wet weight only. So in order to determine the wet weight moisture content, we will dry the sample in an oven at 105 degrees Celsius. So this will ensure that the water is completely evaporated, and then we will calculate the difference in the sample before and after the drying. So similar to the previous formula, we will have A and B, where A is the weight before drying and B is the weight after drying. So if I say A minus B, then what is this? This is equal to the weight of water. So whatever A minus B divided by A into 100. So this is the same as this formula. Whatever wet weight was there, we will subtract. We will subtract the dry weight from that, and then we will determine the weight of water. Okay. Now coming to chemical properties. Can someone list out the chemical properties of solid waste? Can someone list out the chemical properties of solid wastes?
मैम हैवी मेटल आएगा और शायद पीएच आ जाएगा केमिकल ऑपोजिशन
Sorry?
हैवी मेटल
Heavy metal. I think there is a confusion between chemical properties of solid wastes and chemical properties of water. So since we are talking about solid wastes, in chemical properties, we don't necessarily have heavy metals. We have other properties like first one being the moisture content, volatile contents and all. So this will come under the term proximate analysis. So this will include the moisture content, the volatile content, ash content, and the fixed carbon content. So moisture content we have already seen. So then volatile content, how to determine volatile content? For this, we have to heat the sample at 950 degrees Celsius for 7 minutes in the absence of oxygen. So what happens is whatever volatile content, volatile solids or volatile organic matter, whatever is there, it will get evaporated and we will be left with only the fixed matter. So the fixed matter will be either ash or it can be fixed carbon. So for determining the ash content, the sample has to be heated at 750 degrees Celsius and that too at for 30 minutes in the presence of oxygen. Now, why do we heat this in the presence of oxygen is that for ash formation, the substance has to get oxidized first. So only when it gets oxidized, one second. Only when the waste will get oxidized, it will get converted to ash. Only when it undergoes combustion. So in the presence of oxygen only combustion will take place. So that is why we need to have air, especially with oxygen. And then we need to heat the sample at 750 degrees for 30 minutes. And whatever residue is there, that is your ash. And then after we finish the volatile, we determine the volatile content and the ash content, there will still be some residue. So that residue is your fixed carbon. So first we will heat the sample at 105 degrees to find out the moisture content. And then we will heat the sample at 750 degrees and then 950 degrees to find out volatile content, ash content, etc. For volatile content, we will heat the sample in the absence of oxygen because we don't want it to convert it to ash. And for ash content, we will heat the sample at in the presence of oxygen. And after determining all this, there will still be some residue. So that residue is your fixed carbon. So this fixed carbon will not get oxidized. So it will be remaining as such. And the sum of all this will be assumed to be equal to 100%. So whatever solid waste is there, that mass is going to be 100%, and that is going to be the sum of your moisture content, volatile content, ash content, and fixed carbon content. And then we have ultimate analysis. Can someone tell me what is ultimate analysis? What is determined using this method?
Ma'am, chemical constituents.
Yeah, like
CHNS.
Yeah, good. So using ultimate analysis, we will determine the elemental composition. So this includes elements like carbon, nitrogen, hydrogen, and sulfur. And oxygen. Sometimes we will determine sulfur, sometimes we won't. So that's why I'm not included here. So in order to do ultimate analysis, we will heat the sample at 990 degrees and then reduce it. So after reducing it, the NOx will be converted to nitrogen gas and it will be let out, and SO2 will also be separated. So then whatever is left out is carbon and hydrogen. So that can also be separated and determined. And then coming to energy content. So, in energy content, there are actually two types of heating values. So, one is the higher heating value, and the other one is the lower heating value. So, the relation between these two is that the lower heating value, or LHV, is the sum of the higher heating value plus the amount of heat required for the vaporization of water. So, what higher heating value and lower heating value signify is that this will tell you the energy that is released by burning the waste. So, this is an important parameter if the plan is to incinerate the waste and use the heat for generating electricity. So, in such cases, it is important to find out how much is the calorific value or the energy content of the waste. So, that is why this will be determined. And then we will find out the leaching properties. Now, leaching properties is important because previously I said leachate will be created when the waste will undergo some kind of degradation. So that's why when we put this solid waste in a landfill, we have to determine what is going to be the leaching property of that waste, what kind of toxins are emitted by the leaching test. So all this has to be determined, and then only we will know if the waste is safe enough to be dumped on the. It is safe enough to be disposed in the landfill or not. So that is done using TCLP test or toxicity characteristic leaching procedure. So this is done using an extraction vessel. And then we have to find out the lignocellulosic composition. Now, why is it important to determine lignocellulosic composition is because generally when you have waste which has a high cellulose content, it will be difficult for the bacteria to degrade. So when you have something with a high cellulose content, it becomes difficult for the bacteria to degrade, and that is why we need we have to determine how much is the cellulose content of the waste. And then we can determine if that is suitable for biodegradation or some other method, etc. And then we have to find the fusion point of ash. So we talked about how ash content is determined by heating the sample to 750 degrees Celsius in the presence of oxygen for 30 minutes. Now, when we heat the sample to a higher temperature, like say 1100 degrees Celsius to 1200 degrees Celsius, then what happens is ash will fuse together. So ash is usually powdery, but when we heat it to 1000 to 1200 degrees Celsius, it will form small solid substances like clinkers. These clinkers are like small stones or rocks which are very firm. They are not powdery like ash. So these clinkers will form. So to test the fusion point of ash, and that is the temperature at which it fuses together, we have to heat the sample for up to 1200 degrees Celsius. Okay. And then coming to the regulatory framework. Generally, if you have any environmental issues, then first the MOEF will make the rules, and these rules will be put into effect by the CPCB or the Central Pollution Control Board. And then the State Pollution Control Board will also make sure that the rules are implemented. And this will also, the role of the SPCB is also to grant environmental compliance, environmental clearance to projects. So that will also be done by the State Pollution Control Board. And then the regional offices of the State Pollution Control Board. So this is how the regulations will be followed. So the regulations will be given by MOF and it will be implemented by the state and central pollution control boards and the regional offices of the state pollution control boards. So the state pollution control boards also they have the power to give environmental clearance by having a committee of engineers, and they will analyze the project and the environmental impact that the project can have, and then it will give the clearance. Okay, any questions so far?
Madam, can you explain me MOEF?
Yeah, this is actually MOFCC, or Ministry of Environment, Forests and Climate Change.
Thank you.
Any other questions? We'll move to the question answer session. So, is my slide visible?
Yes,
Yeah, madam.
So, the first question is, hydrocarbon gases can be stored in which of the following containers?
Option C, madam.
Yeah. So, C is the correct answer. That's because hydrocarbons or any organics will easily react with glass, ceramics, and aluminium containers. So, PVF is generally unreactive to hydrocarbons. And that's why if you use PVF containers, whatever hydrocarbon gases are there, they will be preserved and they won't react with the container wall. Okay, next question. High volume sampler shows the highest sample efficiency for which size of particles? Any answers? Okay, the correct answer is C. So it will have 99% efficiency for particles in the range 0.3 micrometer. And this can be, high volume sampler can be used for measuring particles in the range of 0.1 to 20 micrometer. and it has the highest efficiency of 99% for 0.3 micrometer particles. Next question. What happens when the sampling velocity is greater than isokinetic velocity in a stack? First, can you tell me what is isokinetic velocity and what is the sampling velocity? So here if you have a stack and the gases are coming out at a certain velocity, and here you have your sampling vent. So here you have a sampler. So the sampler also has to maintain a certain velocity to remove the gases from here. So if we assume that the sampling velocity or the velocity with which the sampler is pulling out the samples, we call it V1, is going to be greater than the stack velocity V2. So that's the question. If V1 is greater than V2, then what will happen? Okay, so generally, if the sampling velocity is greater than the isokinetic velocity, then the concentration of the finer particles will be higher. That's because when you have fine particles, the fine particles means very small size particles. So these particles, when compared to the large size particles, the small size particles will not have a weight. I mean, their mass is not very significant. So they will move in the direction of the gas or the wind. So if the sampler is going to have a higher velocity and it is going to pull the particles, it is going to apply a suction and it is going to have a higher velocity, it means that all the small size particles will easily enter the sampler, and compared to the heavy particles, the lightweight particles will be more in the sample. So that is why we say that when we sampling velocity is greater than the isokinetic velocity. I'm sorry. So that's why the concentration of the fine particles will be higher. Okay, next question is acidification of sample is required for which of the following pollutants?
BOD.
BOD, no. Any other answers?
B option madam, chloride.
Fluoride, B.
No. The right answer is option D, metals. So generally, they are acidified, and the reason behind this acidification is that to enable their shelf life. So acidification will ensure that the sample can be preserved for at least 6 months. Sorry, it will ensure that the sample is preserved for 6 months. Okay. Next question. Volatile solids in a water or wastewater sample are determined by heating the sample at. We just discussed this.
950, madam. Option B.
No, actually 950 degrees is used for measuring volatile solids in solid waste.
Option A.
Option?
105 degrees. Option A. 105 degrees centigrade.
At 105 degrees, the water will evaporate. So that is incorrect.
Ma'am, 550 degrees Celsius.
Yeah, that's right. So option C is correct. So what we do is we will heat the sample. We will first heat the sample at 105 degrees, and we will remove all the water by evaporation. And then we will keep the sample in muffle furnace, and we will heat at 550 degrees Celsius. And whatever difference in weight is there before and after heating at 550 degrees Celsius will give you how much volatile solids were present. So that will give you the weight of the volatile solids. So sample is heated at in a muffle furnace to determine the volatile solids. Okay. Next question. Which of the following devices is used to measure the higher heating value?
Muffle furnace.
No, that's not correct.
Ma'am, bomb calorimeter.
Yeah. So, in order to find out the higher heating value, we will use an instrument called a bomb calorimeter. So, in a bomb calorimeter, what we do is we will take a sample, maybe 1 gram or 1 gram of sample, and then we will heat it. We will just, let it combust, and imagine the waste is getting combusted in this chamber. So this chamber will be surrounded by another chamber which will have water. And then at one point you will also have a thermometer. So the basic idea is that whatever heat is produced by the combustion of the waste, so the heat will escape and it will come to the water, and the thermometer that is here, it will measure the change in temperature with the combustion. So at some point the temperature of the water will rise. So this rise in temperature will correspond to the combustion and the energy release by the waste as it burns. So this apparatus is called a bomb calorimeter. So the energy that is released is dependent on the like how how much calorific value your waste will have. So that is determined using this apparatus. Okay, ask the following. Can you tell me which is the correct answer? So on the left we have different categories of recycling, and on the right we have the meaning for each of the categories. So can you tell me the right answer? What is primary recycling? In primary recycling, the product characteristics are similar to that of the original product, meaning that there won't be any change. So, imagine if you have um, a wooden box. So once you are done and you throw it, you want to recycle it, you will just rearrange the wood pieces in a shape that fits you. You can just rearrange the wood pieces in a shape that you desire. So it means the characteristics are similar, but the usage is different. So instead of a box, maybe you have something like a plank, or maybe you have a frame. So still the characteristics are the same, but slightly it is different. Now, when it comes to secondary recycling, the product characteristics are different from those of the original product. So your product is it is not the same thing, it is completely different. So after recycling, it becomes a different kind of material. So that,
Correct answer to second.
sorry,
B.
huh?
Nice. Ma'am, B part. A.
Um, can you repeat?
Ma'am, B part. B
B
option.
Option B. You mean
B,
option
ma'am.
2?
Yes, ma'am.
Yeah, that's what I'm saying. Like option 2 is the right answer, so that's why I'm explaining all this. Since nobody answered, so I proceeded to the answer. And tertiary recycling is production of basic chemicals from the plastic waste or scrap. Like you can recover noble metals from, you can recover lithium from lithium batteries and so on. So all this will come under this category, tertiary recycling. And quaternary recycling is retrieving the energy content of waste scrap by burning. So this is like incineration, so where you just burn the waste and you generate the heat, and that heat can be used for a variety of activities. Like it can be used to generate electricity, or it can be used for cooking. So this will come under quaternary recycling. Okay, so with this, we have come to the end of this live class. So if you have any questions, please let me know. So if there are no questions, then we conclude the session. Thank you all for joining.
Thank you, ma'am.
Thank you, ma'am.
Thank you.